We've solved the Schrödinger equation for the hydrogen atom. We got wave functions and energies, and we're able to look at those. Now let's go to the next element in the periodic table, that's helium, and see if we can apply our approaches we use for the hydrogen atom to the helium atom. And we'll find, just to give you the bottom line here, no, we can't use it. We'll have to use approximation methods. But just let's see why that is. So our model is we now have 2 electrons in the helium atom, and they move around the helium nucleus. The helium nucleus now has 2 protons and 2 neutrons. We'll do the helium-4 atom. Well, let's see if we can describe this classically. Okay, so our system is, we have a helium nucleus. It has a +2 charge. And then around this, we have 2 electrons with a negative charge. And these electrons can move independently around the helium nucleus. So we have 3 particles to keep track of. Let's denote this as electron 1, and the distance between the electron 1 and the nucleus, R1. We'll denote this as electron 2, and the distance between the electron and the nucleus for electron 2 is R2. But then we have to worry about this interaction here. This has a negative charge and this has a negative charge, so there'll be some sort of Coulombic repulsion there. So we'll give this distance R12, the distance between the 2 electrons. All right, so let's look for electron 1. The Hamiltonian, the classical Hamiltonian, will have a kinetic energy term for that, plus a potential term. So the kinetic energy term will just be the momentum of the momentum of the first electron squared over 2 times the mass of that electron. Plus, now just let's look at this potential interaction, the electron-nucleus interaction. That's equal to Q1, the charge on the electron, which is minus E, times Q2, which is the charge on the proton, which is plus 2E, divided by the 4 pi epsilon naught times the distance between the 2 charged particles. So that's just minus 2E squared. The same thing for electron 2, exactly the same thing. The Hamiltonian is the kinetic energy plus the potential energy, which we denote by V. Okay, and kinetic energy is the momentum of the second electron divided by 2 times the mass of that electron. Minus, I'll just rewrite this, 2E squared over 4 pi epsilon naught R2. And then third, we have the electron-electron interaction here. So that is just a Coulomb. This is let me just write this as electron 1, 2 interaction. The Hamiltonian for that will just be the potential energy. All right, this has a charge of minus E. The second electron has a charge of minus E, and the distance between them is R12. So this is a positive E squared over 4 pi epsilon naught R, the distance between the 2, R12. So the total Hamiltonian, the total energy, is this Hamiltonian here for the first electron plus that of the second electron plus that interaction between the 2 electrons. So there's the Hamiltonian, the classical Hamiltonian for this model, 2 negatively charged electrons moving around a nucleus that has a positive +2 charge. Okay, so now we're going to take this Hamiltonian and transform it into quantum mechanics and see what we get.